Hey. All right, so good afternoon, everybody. Thanks again for the organizers for giving me a chance to speak. When I was thinking about what I'd like to speak about, I decided to come back to a sort of a body of work that I'd done with these collaborators here, which is a little bit more in line, as we'll see, with the themes of this workshop. Basically, the fundamental question that I'm going to try to address here is, so basically, whatever early universe dynamics gives rise to the dark matter, that gives rise to the dark matter phase space distribution, and this can, of course, evolve over time due to self-interactions or due to decays of particles into lighter particles and things like that. But that leaves an imprint on the matter-power spectrum. And the question is, since the matter-power spectrum is what we actually observe, to what extent can we go back and learn about the early universe dynamics or reconstruct that early universe dynamics from the properties of the matter-power spectrum? And this is kind of challenging because, of course, this map is not necessarily is clearly not invertible and not necessarily even one-to-one. However, what I'm going to try to convince you of in this talk is that under certain assumptions, there are some interesting things that you actually can infer, especially in the case when the effects on the matter-power spectrum are basically due to free streaming. Okay, the basic starting point is as follows here. So to describe, I'm going to be looking at, because I'm going to be looking at free streaming, the velocity distribution or the phase space distribution of dark matter. And this very basic starting point is because distance scales in cosmology scale like this in an FRW universe and momentum scales like this, d log p, where p is the momentum by dt, is equal to minus h, the Hubble parameter, and the physical number density looks like that. So the co-moving number density, of course, looks like this. We multiply by a cubed. Now, if we convert this physical number density, an integral over p here in spherical coordinates, to an integral over d log p, this little quantity in a box here is sort of the log space version of the dark matter phase space distribution. So basically, we're going to call this thing g of p. This is going to be our log space phase space distribution that I'm going to focus on for the remainder of the talk. Basically, the area under the curve is proportional to the co-moving number density. And so this is an object that I've just defined. Why is it interesting? The reason that's interesting is that it evolves with time in a particularly straightforward manner when there are no sources or sinks. In particular, you can see g of p really does not evolve in shape at all, but merely under the influence of redshifting, effectively shifts just to lower values of log p. So basically, it acts like a milk carton that you set on a conveyor belt on the supermarket, and it just keeps going in the absence of any sort of sources or sinks. Of course, when you have sources or sinks, things change, but this at least gives us a handle on how to deal with these changes. So let's imagine, just for illustrative purposes, that we have a simple toy model of three fields, phi 2, phi 1, and phi naught. I'm labeling naught 1 and 2 in order of increasing mass. And let's imagine that they have masses in the appropriate proportion so that each one of them can decay to lighter particles of any of the other species. So we'll also work in the instantaneous decay approximation. So each phi decays completely at its lifetime. So, okay, if we start with everything in the heaviest field here, all of the abundance in the heaviest field, it redshifts, and then at this instant where we do the instantaneous decay approximation, decays into two daughter particles right here. And those two daughter particles, then they redshift. And then once we get to the decay time of this particle here, it decays and leaves another deposit on the conveyor belt of the lightest particle. So now, because we have this sort of decay chain with multiple different steps that have multiple different timescales, we have a complicated multimodal distribution here that evolves, again, with time in a trivial manner now that there are no sources or sinks. So this is the kind of dark matter phase space distribution you can get in scenarios where you have these kinds of decay chains and the interactions, the scattering interactions among the particles are too weak for them to thermalize. So these are going to be the kinds of scenarios that we're going to take a look at because these are kinds of things that can arise in, for example, hidden valley scenarios or other types of scenarios like this where you do have a lot of cascade decays. So what can we say about complicated phase-space distributions like that in scenarios under which they arise? And by the way, although I just want to emphasize that although I, was making the instantaneous decay approximation and things like that beforehand, and by the way, there are all sorts of other subtleties like different parts of the dark matter velocity distribution have different time dilation factors in the cosmological background frame. There's all sorts of subtleties I was glossing over. If you incorporate those all, you still get these kinds of complicated multimodal distributions under certain circumstances. So these are not crazy things to look at. Okay, so let's examine here how we might find evidence of such multimodality in the matter-power spectrum. All right, so matter-power spectrum, what we're going to assume here, again, is that basically free streaming, so when we have particles with sufficient speed that they can escape from gravitational potential wells and suppress structure on small scales, that's going to be the dominant effect, that's going to be our assumption, on the matter-power spectrum at small scales. So we'll define the transfer function in the usual way. So this is P of K divided by what we would get for purely cold dark matter. And let's see what we can learn from this. Okay, so the free streaming horizon for a particle of mass m and present-day momentum p in an expanding universe, if the universe weren't expanding, we would just say, well, it's the velocity times time is basically the distance that it travels, and therefore 1 over that with some 2 pi factors is basically what the, that would be what the corresponding wave number would be. And so here is this order 1 factor, and here is 1 over what you would get for velocity times time. Of course, the universe is expanding, so we need an actual integral rather than just multiplying v and t with a scale factor here. And if we convert the integral to an integral over the scale factor, this is what it looks like. Okay, so the usual approach that you're probably familiar with that people use here is to basically kind of take an average velocity for the whole dark matter velocity distribution or phase space distribution and say, we're going to define our free streaming scale, quote unquote, by using this average dark matter velocity and treating it like this. That's going to give us our horizon k here, and that's what we'll go with. What we are going to do here is I'm going to, by contrast, consider a somewhat unorthodox procedure here, where we instead regard this horizon k function of p as a functional map between p and k. So for any given p, present day value of the particle momentum, this is going to give us a k. This is a map that we can invert. This is an invertible map. So therefore, this inverse map from k gives us a p. What this allows us to do is something equally unorthodox. We can define a phase space distribution for dark matter in k space by taking the dark matter phase space distribution, the log scale version of it, the g, and then plugging in the momentum p that we would get by taking the inverse of this horizon function and operating it on a given k. So that's what we'll call g twiddle of k is our k space phase space distribution here. And of course, there's a Jacobian factor from the transformation as well. So what we're going to see then, we're going to define this, and then we're going to play around with it and see what's useful about defining this weird k-space phase space distribution for dark matter. Okay, so first of all, let's and again, we're just playing around here, totally empirical. Let's consider the case of a simple G of P distribution, which is unimodal, single log normal peak with average momentum bracket P and width sigma. And we'll begin by fixing this mean value P and sigma and varying just the normalization of the peak. So we're going to assume that everything, all the abundance that's not associated with this peak is in a purely cold dark matter component. So here are what the G of P distributions look like here for this. This is our log normal peak. Here in this right panel, these corresponding colored curves to this are the transfer functions that we would get out of these. These dashed curves here represent the G twiddle, the k-space version, or the version of the G of P. So here, what we basically see is scanning kind of from left to right over this distribution. Basically, the transfer function kind of remains at unity up here, but once we scan through the peak, things change, of course. And they are going to drop, and one of the things that we notice here, well, we notice a couple things. We notice that the dark matter acoustic oscillations here going around the wiggles become more pronounced when omega, the fraction of the abundance here associated with the peak is big. But we also notice that the slope here at large K, once we scan through this feature, depends on what omega was. Okay, put that in the back of your mind. Let's take a look at a couple of other things. Now let's hold omega fixed and vary the width sigma of the peak. So here are a bunch of G of P distributions with the exact same abundance, but different sigmas, different widths. Here is what these things look like, the G twiddles, the corresponding G twiddles as a function of K. Note that large momentum corresponds to small k, so this is why these things look flipped over here. All right, here are the corresponding transfer functions. What do we notice? What we notice is that, interestingly enough, although the amounts of suppression are different, the slopes as we get scanned through this to go to large K are the same. So what this teaches us is that the abundance associated with a peak in G twiddle correlates with the suppression in the transfer function. Not with the suppression in the transfer function, but rather with the slope. It's the slope that's correlated with this. Okay, interesting. What if we had a complicated bimodal distribution that looked like this? Let's see if this bears out. So here's a bimodal distribution, and what we're going to do is assume that all of the abundance is associated with either this peak or this peak. So this peak we have the green one, we have the low momentum peak, the cooler peak here. Is having the majority of the abundance. The blue, the higher P peak is having the majority of the abundance, and the red is in the middle. Again, we're going to go over here. So the G twiddles, these dashed lines. So again, this is flipped. This feature over here corresponds to this feature corresponds to this feature. And what we see is, once again, as we scan through each peak, even though it doesn't have all of the abundance, what we notice is that the slope here is correlated with the amount of abundance that we scan through to get to that particular value of K. And indeed, once we scan through basically the entire abundance here, this slope and this slope look very, very similar here because there's hardly any abundance here. And so we can see again that it's the change in slope here that's correlated with the abundance in G twiddle. Okay, interesting. So what can we do with this? Well, okay, if the slope of the transfer function indeed is correlated with the total number density of particles which can free stream at that value of K, particles with momenta P greater than this functional map of K, inverse functional map of K, what we can do, it makes sense to define what we like to call the hot fraction function. And here is the hot fraction function. Basically what this is if we integrate all the way from very, 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 very low K, so minus infinity in log K, basically 0 in K, all the way up to some value of K, and then normalize to the entire integral over G twiddle over all K, that's our hot fraction function. So it goes between 0 and 1. What this represents is the fraction of the abundance that is effectively hot or can free stream on a particular value of K. So for example, if we, like right here, basically all of these particles, they don't have enough, the F here is 0, they basically, hardly any of them have enough momentum to free stream over a K that corresponds to a feature, say, this big. However, as we increase what K is, F of K, so here are all the particles, the abundance associated that is hot on that value of K. These are the things that could free stream out of halos associated with this distance scale. And as we increase, we subtend more abundance here under the curve, and the hot fraction increases toward 1. And eventually, as we get to smaller and smaller scales, all of the particles can free stream out of scales that are the size of a dime on present day. So basically, the hot fraction in that case goes to 1. Okay, what we have seen, the assertion here is that f of k, the hot fraction function, is associated somehow with the slope of the transfer function. So empirically, from numerical investigations using the class code, we can basically take a look at what this relationship is. And here is a simple empirical relation that we have basically derived between these two quantities. So the derivative of the logarithmic derivative here, d log t squared by d log k, is basically equal to the hot fraction function squared plus 3/2 times of the hot fraction function, just empirically. And taking the derivative of both sides gives us a relationship, therefore, because f is basically the integral of g twiddle over k. This gives us an expression for g of k in terms of derivatives of the transfer function. Of course, this is a completely simple empirical relation that we've derived. This can obviously be further refined by, more in-depth analysis, machine learning, etc. But the point is that this is a relationship that's fairly robust and that exists. So, and a lot of this work, by the way, was done by Fei Huang, who is in the audience here. So in order to determine how accurately this procedure works, what we would like to do is play around and see how well it actually is able to reconstruct the dark matter velocity distribution from different kinds of transfer function that we would get from those different kinds of velocity distribution. Great, thanks. Okay, so what we're going to do then is define we're going to see if we can find a concrete example model that we can use that will give us a variety of different phase space distributions that we can then use class numerical simulators to be able to create different transfer functions and then see if our reconstruction procedure does a good job of reconstructing. So again, this model is a simple model that we are using. The goal is to analyze the procedure, right? The goal is not to believe in the model. So I don't need it to be a compelling UV complete theory of nature. I just need it to produce within its parameter space a lot of different G of P's. So here's the model. I won't go into details with it. It's a bunch of scalars. They have different trilinear couplings. And their masses scale across this ensemble of different scalar particles like this. And the couplings scale in this particular way. Here are a bunch of different combinatorial factors and things and a heaviside function and all that and an overall mass scale because these are trilinear. Here's the important thing. Here, these two factors here. So this quantity here represents the gap between the parent and daughter masses. So the parent mass minus the sum of the two daughter masses. And this represents the gap between the two daughter masses. And we're taking these to the power of two different constants here, R and S. What R basically represents, so this is the gap between the parent and the daughter masses here, if we're raising this factor to some power, this is, if R is big, this favors highly exothermic decays. If R is really small, it's minimally exothermic decays. If this S parameter is really big, keep in mind there's a minus sign here, it favors symmetry among the daughters. It favors the daughter particles having very similar masses. If S is very small, S is negative, it favors asymmetry among the daughters. These are the kinds of broad brush properties that we want to analyze here. Okay, so we can calculate decay chains and do all sorts of fun things like that. And basically the overall upshot here is in certain situations, we end up with situations where there are different decay chains that all have, significant probability down from the top of the tower, if that's initially populated, down to the bottom, which have very different time scales and basically can put deposits on our cosmological conveyor belt at very different times and give rise to a complicated multimodal dark matter velocity distribution. Here's what they look like. So here, these are basically unimodal distributions that look like this. Here are complicated multimodal ones here. So the question is, how well does our reconstruction conjecture work? Here's the upshot. You can see that, of course, obvious. So the blue curves are the actual things that we are feeding into class. The red curves are the reconstructed G-twiddle distributions. And we can actually see that although obviously this is not perfect, we do reconstruct very robustly the broad brush features of the dark matter velocity distribution in all cases. Why is this interesting? Well, if we in the near future, gain access. This conference is all about, you know, the future data, you know, cosmological surveys and things like that. Forthcoming 21 centimeter forest data and can, in principle, give us access to higher values of K, which means that we could be in a position where we could start to need techniques like this, which would allow us to be able to take information that we see in the matter-power spectrum and possibly infer something about the methods that the mechanisms that produce the dark matter. So this is indeed so this could indeed be an interesting tool in the dark matter analysis toolbox. And there are other implications here for cluster number counts, satellite counts of having dark matter velocity distributions that have very non-trivial shapes and things like that. But I'll leave that for another day. If anyone's interested, feel free to come talk to me at the coffee break. So I'll just put the summary. I basically have 0 minutes, I'm guessing. Okay, great. In that case, perfect timing. I'll put the summary slide up, and if you have any questions, let me know.